Folks, we're here to talk about Ampere's law. And as a means to do so, I'm actually going to talk about Gauss's law. All right, so Gauss's law, as you remember, do you? Gauss's law is a convenient way to express the strength of electric fields. All right, and the way that you do that is, well, let's assume that this tiny little thing is a point charge Q. All right, and what we want to do is write an expression for the electric field anywhere near that charge. Okay? Well, this is trivial because we know what the field is near a point charge, but, let's start with the simple. Okay, so what Gauss's law says is that there is this quantity called, it's called electric flux. And electric flux is it's kind of like, well, by definition, it's the scalar, the dot product of E and dA, or the surface integral of that. And what that means is, well, if we can define a surface, right, that has an area, well, that has lots of little areas on it that we could add up all of those areas and find the area of a surface. And especially if we could do that, and we could define a surface where, well, if E was, if E was constant everywhere along that surface, and if all E and dA vectors were parallel, well, first of all, if all those vectors were parallel, that dot product would turn into this product. And then if E was constant everywhere, what we could do is pull that out of there, that constant out of there. And then what we have to do is be able to evaluate the surface area of a shape, a three-dimensional shape that we choose. So that means we have to be able to choose a shape that we're aware of the area of. So what we could do is say, well, you know what? Here is such a surface. That my Gaussian surface is a sphere that's concentric with this point charge, or that is where the point charge is at the center. And then all our little dA vectors point outward everywhere. Well, we know that electric field points outward everywhere. And so if we define this surface to have a radius r, well, all our electric field lines come out like this. And so there's a net flux outward. That's what we would say. There's a positive, at least there's a positive net flux. I don't know if we could say net flux is outward. There's a positive net flux because, well, all these E's and A's are in the same direction. So, we multiply the scalar product of the magnitudes of those vectors. So, well, and what Gauss's law says is that this amount of flux depends, or is directly related to the amount of charge that we enclose within our Gaussian surface, and there's a constant of proportionality that has to do with the degree to which electric fields are able to be created in different substances, called the electric permittivity of free space. So what we can do is, basically we'd like to say, okay, what's the surface integral of our sphere? Well, that's 4 pi r squared. We're aware of what the surface area of a sphere is. And that's equal to, so now we have our net flux, E times 4 pi r squared. Well, that's equal to, per Gauss's law, Q enclosed over epsilon naught. And that says that we can use this to write an expression for the field, Q enclosed over 4 pi epsilon naught r squared. That's the same thing as writing K, which is Coulomb's constant, Q over r squared, because K is 1 over 4 pi epsilon naught. Okay? And this tells us, sort of, quote, what we know. We know that point charges create electric fields that the magnitude of which is inversely related to the square of the distance from the charge. Yeah? So, would you use Gauss's law to find the field made by a point charge? Probably not, because you already know that answer, but at least Gauss's law bears that out. All right? And we can do that with more complex charge distributions, like say this was a charged insulator. right? A uniformly charged, or even an insulator with varying charge densities. Well, what you can do is say, well, if I want the field inside, let me define a Gaussian surface inside here, and I can write an expression for Q enclosed in here, and I can, so we can find fields, or we could say, well, now outside, how much charge is enclosed, and then for what's the field look like outside. That's what we've used Gauss's law to do. Ampere's law is a way to conveniently, or more easily, express the strength of magnetic fields when electric currents, I'll say, are well, I guess have some geometric conveniences. So here's a straight current carrying wire, right, and it carries current this way. Okay. Well, Ampere's law is very similar in structure, right? Here's Gauss's. Gauss's is surface integral E dot dA is Q enclosed over epsilon naught. All right. Ampere's law looks structurally very similar to that, except of course not electric field. What we do is we look at magnetic field, and well, it's not a surface integral because, well, magnetic field lines are continuous. They have no ending. All right. Electric field lines start and end on positive and negative charges respectively, but magnetic fields have no ending. All right. The magnetic field around this wire looks like this. It comes, well, it's a circular field that oh no, it's a circular field that looks something like this, where this field is coming down in the front and going up in the back, and it's coming out of the page up here and is going into the page down here, right? That's a right hand rule thing. We put our right thumb in direction of current and our fingers of our right hand wrap in the direction of the field. So this field, I've drawn a break in it just to give you some like kind of perspective-y look at it here. So there's no such thing as a surface where we would have magnetic flux that was other than zero. Okay, if you take any surface, right, here's an enclosed surface. It's a bubbly blob. Well, any line that comes into our surface comes out because magnetic field lines never end. So there's actually a Gauss's law for magnetic fields that says magnetic flux has to be zero. All right, so Ampere's law doesn't use magnetic flux. Ampere's law uses something different. What we could do is say, well, if there was a loop, not a surface, but a loop, a two-dimensional loop, where, well, we can say that along the loop there are lots of little dLs. Well, if we could pick a loop that had characteristics such that B and dL vectors were always parallel, that means this would turn into, well, look, this is now called a path integral. So everywhere along our path, if B and dL were parallel, that dot product would turn into this scalar product. And, well, if B were constant everywhere, then we could pull that B out of this path integral, and then we just have to take some sort of two-dimensional path where we are aware of how to express the length of that path. Well, guess what? Such a path looks exactly like this. That's called an Amperian loop. Okay? And what Ampere's law says, Ampere's law says that that product B dot dL depends, guess what? Not on charge enclosed, but on current enclosed. And by enclosed, I mean that goes through our loop. And, well, of course, not this electric permittivity of free space, but the magnetic permeability of free space. And we've seen, perhaps if you've looked at Biot-Savart, that law, thank you very much, you'll notice that while we have, 1 over epsilon naught for Gauss's law, we have, or for Coulomb's law, we have mu naught as in a kind of numerator. So this looks like this, mu naught I enclosed. Okay, so if we can do this and say, well, I hereby choose a loop that has a radius r, well, I know how to integrate the total length of that loop. It's 2 pi r. And we're saying, well, that is equivalent to mu naught I enclosed, or what we're really saying is this product is directly related to how much current runs through that, runs through our loop. And then look how easy it is to write the field created by a single current carrying wire. Easy peasy. Where you can use Biot-Savart to do the same thing, but boy does it take a lot of steps. And holy mackerel, the integration's not the hard part, but getting everything in the same terms, boy, that's a pain in the butt. This is simple. Right? This is B as a function of R. And what we get is an inverse relationship between field strength and distance away from wire. Right? Right. Well, guess what? We can also then do that for more complicated cases, like this. What if this is a big fat wire with, lots of charges that are moving through it? Well, we could say, well, inside the wire, we could choose a loop. Outside the wire, we could choose a different loop. And we can, use what we know about differences in enclosed current to look at differences in physical structure, I guess I'll say, of magnetic fields. Okay, so there are a few different types of current carriers where Ampere's law is useful to find magnetic field strengths. But again, you have to be able to do something similar to what you do with Gauss's law, in that we have to be able to say, all right, I can pick a loop where all DLs and Bs are parallel. I can pick a loop where I know that B is going to be constant everywhere along that loop. So those are things that can't be done in all cases, but they can be done in some cases, like long wires of current or other stuff that we'll get to at a later date. But that's fundamentals on what we call Ampere's law. Sound good? Thanks, folks.